Yellowstone and Grand Teton National Parks, Geological History, and Climate Evolution. According to National Parks, The American Experience, 5th edition by Alfred Runt, the backdrop of Yellowstone was something to brag about and must be protected. On March 1, 1872, President Ulysses S. Grant signed the Yellowstone National Park Protection Act, establishing Yellowstone as the first national park. It was 3,500 square miles with a 7,900-foot elevation and 3 territories to Grand Teton's 484 square miles and 13,770-foot elevation, established on February 26, 1929. We can see in Figure C20, Grand Teton occupies a smaller horizontal scale. This is Yellowstone National Park and a few of its many geological features. Figure C9 shows the Steamboat Geyser located in Norris Geyser Basin, originally being considered dormant according to the National Park Service referenced by the Smithsonian Associates. Figure C15 shows the Grand Prismatic Spring located in the caldera. C17 shows the Mammoth Hot Springs formed by volcanic explosion. It contains large quantities of limestone according to the article Mammoth Hot Springs Trail. Figure C7 in the bottom left shows a U-shaped glacial canyon in Grand Teton, one of the 2 types of canyons in the park. C7 on the right depicts limestone with crinoid marine fossils from the Paleozoic era. Figure C7 in the top left is the southern Teton Range. The range has layers of sedimentary limestone, shale, and dolomite. Yellowstone is made up from more gneiss and schist, which, according to geology, Yellowstone National Park, was shale or sandstone prior to metamorphism. Yellowstone is known for its explosive caldera. Initially a hotspot formed, and Yellowstone as volcano states that 3 separate eruptions formed the caldera. The first was large and released basalt and rhyolite. The second was smaller, and the third eruption was 600,000 years ago and collapsed the crust, forming the caldera. Figure C21 shows a timeline of calderas and resurgent domes. The park has abundant hydrothermal activity, as Schiller, Whitlock, and Brown write in Holocene Geoecological Evolution of Lower Geyser Basin. As for the Teton Range, formation gneiss began to crack, allowing magma to seep through. This happened 2.5 billion years ago. It cooled to form crystals or igneous granite, as reported by discovered Grand Teton in Geological Timeline Teton Geology. This formed high peaks in Grand Teton, Middle Teton, and Mount Owen, as shown in Figure C14. Earthquakes at the Teton Fault played a huge part in forming the Grand Tetons, allowing the land to uplift and fault, while Jackson Hole settled into a steep valley, according to Geology of Grand Teton National Park, U.S. Geological Survey. About 775 million years ago, the range stretched. This cracked the gneiss and granite, allowing more magma to seep through and creating diabase igneous rock. The most recent development was Pinedale, Wyoming, a private purchase established before Grand Teton. This glacial period buried and eroded older landscapes as outlined in the geological timeline by discovered Grand Teton. Image C10 shows Pinedale on the map in comparison to Jackson Hole and Grand Teton National Park. According to the Smithsonian Associates in Geological History of Yellowstone, 500 million years ago, Wyoming was covered by a shallow sea. Volcanics began to arise 50 million years ago, as seen in Figure C21. The Precambrian era allowed the continental foundation to build. In the Cambrian period, deposition of sediment began, and the Cenozoic era provided mountain building and glaciation between both parks. Yellowstone eventually became flatter than Grand Teton due to erosion. The glaciers created the valley and washed away soil in Grand Teton. This affected the ecology and ecosystem as it began to change. The force that lifted the range is actually considered more geologically recent, based on findings from Geologic Timeline by discovered Grand Teton. Figure C7 depicts a 2.7 billion-year-old metamorphic gneiss in the park. Figure C11 shows the retreating Middle Teton Glacier. The parks are beginning to experience shorter seasons and variations of weather patterns. Yellowstone gets snowfall in only some elevations, and scientists are working with the IPCC have predicted more rainfall rather than snowfall, as reported by the UCAR in predictions of future global climate. The data collected by the National Park Service in Climate Change Yellowstone National Park states that the changes we're seeing are at the hands of humans and natural forces. In Figure C16, we can see the melting ice patches, which are revealing old, dead, white bark trees. The Teton Range is experiencing drier periods, which makes it more susceptible to fire, and right now glaciers are retreating as seen in Figure C13. Some of these changes are caused by natural forces, while others are caused by human interaction, according to Larson, Finkbinder, and Abbott in Deglaciation and Post-Glacial Environmental Changes in the Teton Mountain Range. A huge factor in changes in Yellowstone National Park is human interaction. As of late, the NPS has had to prevent people from interacting with wildlife and overall ecosystem. As stated by the Nature Conservancy in Greater Yellowstone, the active tourism has created mass traffic resulting in disease and pollution. Image C6 shows bison wandering through traffic as they become accustomed to visitors. Yellowstone attendance has increased by 40% according to the Environmental Protection Agency and Climate Change Connections Wyoming. Figure C2 shows how terrible traffic has become. Figure C1 shows the haze over the region from neighboring polluters in Grand Teton. The USR Center for Science Education states that the NPS is working to solve the effects of air pollution. With an earlier thaw, there will be an impact on forage, water flow, and fire protocol as the ecosystem gets drier. Schiller, Whitlock, Brown, in Holocene Geoecological Evolution of Lower Geyser Basin, write, quote, changes in climate and fire regime have long been recognized as drivers of the post-glacial vegetation history of Yellowstone National Park, but the effects of locally dramatic hydrothermal activity are poorly known, unquote. Image C4 shows the evolution and path of Yellowstone's hotspots, which scientists are now considering for climate change. Yellowstone is still going through active erosion as seen in figure C19. The Precambrian rocks are beginning to erode slowly and sedimentary rocks are being deposited, as stated by the National Park Service in Yellowstone National Park. The caldera is still active. Grand Teton's tectonic activity assists in glacial carving, uplift, and erosion. Figure C5 shows the fault lines within the boundaries of Grand Teton. Red is the fault line, while green is base of Grand Teton. Deglaciation and post-glacial environmental changes in the Teton Mountain Range by Larson, Finkbinder, Abbott, and Austin says, quote, the transition to non-glacial sediments marks the onset of Holocene conditions at Jenny Lake and reflects a shift towards warmer summers, increased vegetation cover, and landscape stability in the Tetons, unquote. Yellowstone and Grand Teton, while close in location, have very different geologic makeups and ecosystems. Their systems are constantly changing through natural sources and human disturbances. The calderas and fault lines are still very much active today, contributing to the dynamic system and evolution.